might hear it first, you might not like it. I'm Radcliffe, and my mission today is to persuade you that if you do data analysis, you should think about doing test-driven data analysis, which of course is the title of my talk, though I did consider other titles. I'm going to start with your indulgence by telling you a bit about how I got to the idea of test-driven data analysis and indeed test-driven development, which obviously is not my idea. And then I'll tell you a bit about how it works, what tools we've got and are developing that might be able to help you, and why I think you should use it. So I guess it all started for me really back a long time ago. As a teenager, I spent all my time basically writing code. First, lots of machine code, lots of Z80 code, and then 6502 code with UC micro. I spent my summer holidays writing code for my local education authority, writing databases and work processes that were used by kids in schools in Hertfordshire. It was interesting stuff. My code was used by tens of thousands of kids. It ran literally thousands of times faster than the code it replaced. Remarkably few bugs were ever reported against it. It produced the same results as the code it replaced, except for where the code it replaced was producing the wrong results. So at the time, I really thought I was pretty hot shit. And then I went to university and did a PhD in genetic algorithms and deep learning, as I didn't know it was called at that time. Formed a company and then stopped coding for 15 years. I started managing developers and data analysts. And then we started tackling a new class of problems, something we called uplift modeling, which there wasn't a known solution for, a statistical problem, which I won't go into. And so at that point, I started writing lots of pseudocode. And then pseudocode wasn't enough, so I decided I needed executable pseudocode, so I started writing Python. And when I did that, I made an extremely unpleasant discovery, which is that writing code is not at all like riding a bike. I found that I had developed the ability to write a page of code and include not only like a dozen syntax errors, but probably half a dozen logic errors. And life was all a bit depressing. But at that time, I was reading a blog by Tim Bray that you may know called Ongoing, and he was advocating this thing called test-driven development. And my understanding of it was that really the idea with test-driven development was that you wrote so many tests and such detailed tests that there was really no place for bugs to hide. And given the coding state I was in, that seemed like a good idea, so I started doing that. And that's what I do to this day. I try to create a really inhospitable environment in my code for bugs, and that's really, I think, the only reason I'm still capable of writing code at all. Well, what you notice I didn't do was read any books on TDD, and so my notion of TDD diverged a little bit from everybody else's notion of TDD. And so what I understand the sort of orthodox TDD process to be is something like this, that you write some failing tests, probably with lots of mocking. You then write code to make those tests pass, or edit code to make those tests pass. Maybe you go through some kind of a refactoring phase where you simplify the code, and then when you want to add functionality or fix bugs or whatever, you write more tests and keep going on this cycle. And if you're really good, you have a continuous integration system running, somewhere to run these really all the time. And some advantages that you have, and of course this is an oversimplification, but some advantages you have compared to doing data analysis are that a lot of the time with other kinds of code, they're fairly well understood inputs, you have a fairly well understood goal and algorithm that you're trying to implement. And certainly not all, but many of the kinds of ways the software can go wrong are fairly easy to detect and be sure about. My version of TDD wasn't really very like this. What I typically did was write some code to produce a result. I never mocked anything, still don't mock anything. So I'd write my code, generate my results, and then I'd spend a really long time trying to convince myself that the code didn't work. And I found a really good mindset for this was the sort of Jeremy Paxman mindset, where you'll remember Jeremy Paxman says that when he's interviewing a politician, his general thought in his mind is, why is this lying bastard lying to me? And that's very much it. It's like, why is this lying data? Or really, why is my pathetic data analysis misleading me? Is what I'm trying to do. And then when I finally convince myself, if I ever do, that the code is working, that I believe the results, then what I do is I take the inputs, I package those together with the function and take the outputs that are being produced by that function, and I turn those into a test. And I tend to call that a reference test. They're usually big. They're much more like system tests than like unit tests. I never made this distinction between unit and system tests. But any TDD would look at mine and say, well, they're all system tests. Well, not all, but a lot of them are system tests. And I definitely write the code before the tests. And I've never really felt like I had very much choice about this, because the things that I'm testing are usually a lot more. But basically, I can't construct the results by hand. The only way I can construct them is by writing another program to construct them, which isn't a ridiculous idea, and I have done that, or find another package that does it. But usually the results then won't be in the same form, so it still doesn't really give you the thing you need to test about. So that's kind of the story, and I apologize for taking so long telling you it, but that's how I came to TDD. And the other thing that's obviously true is the context in which I was doing my TDD was developing analytical software and indeed doing data analysis, but I only did the TDD part for the development. So what about data analysis? Well, the trouble is, when I do data analysis, or when I see other people doing data analysis, it doesn't really look very much like this. It typically looks something more like this. It always starts in the context of a data set or a set of data sets. And in fact, the first part is usually scrabbling around trying to collect some data that you can use for your analysis. And then, then it starts. You try and, you never get a good data dictionary, right? The data's never clean. You never really know what you're dealing with. And you look at it and, you start to question your own sanity. You start to question the competence of the people who put the data together. You discover that, there are probably no join keys, or maybe there are half a dozen different join keys, but you don't know which one's reliable. You find that some of the data's missing, some of it's actually been synthesized, some of it's real, some of it's in imperial units, some of it's in metric units. And it's just like this horrible process where you're going around trying to understand what the data means, what it's capable of supporting in terms of analysis, and what you can do with it. And then eventually, if you're diligent and lucky, maybe you do come up with some analysis that you believe is valid and that you believe the outcomes of. Or maybe in reality you just run out of time and you either you take a decision about whether to ship it or whether not to ship it. But it's very different from from the nice process we had here. So I have a friend, Patrick Surrey, who said to me one day a few years ago, we do test-driven development, shouldn't we also do test-driven data analysis? And as soon as he said it, we both knew this had to be the answer, this had to be the right thing, we needed some of that goodness. And the only problem was we had absolutely no idea what test-driven data analysis meant, or even could mean. Now, if it had been today, we'd have been all right, because we could have channeled our inner Theresa Mays and said, well, test-driven data analysis means test-driven data analysis. But we didn't know you were allowed to do that then, so we actually went back and tried to figure out, I mean, all kidding apart, the high-level idea hopefully is clear, right? We wanted to take the ideas from TDD and transfer them from the arena of software development to the arena of data analysis. As the lawyers would say, mutatis mutandis, or if your Latin's not up to scratch, those things which need to be changed having been changed. So all that leaves us with is, well, what needs to be changed? Well, for me, it all starts with correctness, right? We do analysis to try and understand things from the data, to try and optimize things, to try and make better decisions. And it's often okay if our analysis isn't exactly right. The whole idea of modeling isn't really about getting it exactly right, it's about getting useful approximations. And it's kind of just as well, given how analysis typically goes. But at the very least, we should try and get the sign right, try and get the general sense of it right, try and get the decisions right. And unfortunately, Sturgeon's revelation is very relevant at this point. When I say Sturgeon, I'm talking about Theodore Sturgeon, not the Scottish First Minister Nicola. And you'll remember Sturgeon's revelation was that 90% of everything is crap. And I think every part of data analysis is illuminated by this revelation. It's certainly as true for TDD as anything else. And the reason I think data analysis is genuinely harder than test-driven data analysis, whatever that is genuinely harder than test-driven development in most areas, And that's because we not only have to worry about bugs, which are absolutely a thing in the context of data analysis, but we also have to worry about the meaningfulness of the analysis. Are we doing meaningful statistical or machine learning on our data, or even just reporting on our data? We have to worry about, if our output is analysis, we have to get the analysis right, so we have to be sure that the inputs are correct and valid. And we have to do our level best to make sure that we interpret the outputs correctly, and indeed that anyone we give the outputs to interprets them correctly. And those are really quite hard. So when I do analysis, when I look at analysis, which I do all the time that other people are doing, it usually, if I regularize it a little bit, looks something like this. The first thing we try to do is just try and understand what are the kinds of errors that you can make in analysis that don't really apply in the rest of software development, or don't apply as much. And so, as I say, you always start on some initial sample of data, and there are various things that can go wrong at this point. You can fail to understand the data correctly. You can fail to understand the domain correctly, and you can fail to understand enough statistics on machine learning or whatever to know whether what you're doing to your data is actually supported. If you get any of those things wrong, we call those errors of interpretation. And I think those are much more prevalent in data analysis than in the other fields. Once you've decided what manipulations and algorithms you want to apply to your data, obviously you have to implement them. And when you do that, you can make mistakes just like, even if you're doing it in Excel, God help us, or or R or Pandas or Python or whatever it is, there's some kind of process where you have to implement it, and you can get that wrong, and that can be bugs. We call them errors of implementation, but those are just bugs. And if you avoid all the really big mistakes at that point, you get to your initial success, right? At this point, you've got some level of success, and that's great. And if you are doing it in Excel, or possibly even if you're doing it in a Jupyter notebook, and you've really been working with the whole data that you want to analyze initially, possibly you've got your result at this point, but in practice most of the time I find you haven't. You've usually worked on a subset, or you've simplified some stuff or whatever, and now you actually have to run the process. And when you run the process, of course, there's another whole set of opportunities to make mistakes. So the first thing is you've now got some analytical process to do the thing that you want to be done. And you can just use it incorrectly. You can type the wrong parameters, you can feed it the wrong file, you can pick up the wrong file, you can think that you've run the analysis when you haven't. All these mistakes are real, happen all the time. There can be a really important thing is if the data that you're running on is not identical to the data that you developed the thing on, then it may be that your analysis isn't applicable to the new data, because it's not a flaw in the process, it's intrinsic to analysis that the decisions you make about how to parameterize it and even what analysis to do depends on the data that you're expecting to get in. And if you get very different data in, your analysis may no longer be valid. And we call it an error of applicability if that goes wrong. And even if you get through all that without making a mistake, you can still misinterpret the results, or someone else can misinterpret the results. And if any of those things go wrong, you don't achieve success. The other thing that happens all the time is, even if this was intended as a one-off analysis, just figure this thing out, figure out who our best customers are, or figure out whether the aeroplane's safe to fly or whatever. Inevitably, someone will say, that analysis you did last month, could you just run it on the updated numbers? Or indeed, turns out the data was wrong. This is the right data. Could you just run it again? And guess what? If you get to do that, then you get another chance to get the last three stages wrong all over again. So TDDA, we'll actually get towards TDDA. One really sobering thing is if you buy into this, if this looks anything like the data analysis that you do, then it's really sobering to put numbers on this. I've put what I think are quite optimistic numbers on how likely we are to get any of these things right. Maybe you're more optimistic or more competent than I am, and you've got better probabilities than this. But rather sobering is if you put these quite optimistic numbers on how likely you are to get through each stage, that only gives you a 32% chance of success first time through. And if you run it through again, it drops to 19, then 11%. And then when you run it again, it really is quite likely that you've forgotten how to use the software or someone else is running the software for you, so you are more likely to say, no. Of course this is a simplification, and maybe it's pessimistic, but I think it's pretty sobering anyway. So what are we going to do in terms of TDDA? Well, what I call level 0 of, or what I'm proposing as level 0 of TDDA is whatever your process is, whatever your process is, for deciding when you're done with your analysis and when you're happy to believe it, or ship it, or to use it, or whatever. Keep that exactly the same as it is now. But capture the input data you developed it on, or if it's too big to capture a subset of the input data. But typically capture the whole input data that you used it on. Make sure that your process is encapsulated in a way that you can run it reliably. And there's a whole field called reproducible research, mostly coming from the academic community, about this. And the idea there is that when you publish papers, you should publish your code and the data as well, so that other people can verify. And that's kind of two-way thing. So make sure that your analytical process is captured in a scripted, runnable form, or at least a documented, runnable form, and also capture the outputs that get produced, and have some kind of a verification procedure, a diff basically, that will tell you whether or not this analysis process on these inputs produce the output that they should, and then run that repeatedly. And what you may say is, well, surely if you don't change anything, it's inevitably you're going to get the same answer, right? And that is so totally wrong. You might upgrade your Python, you might upgrade your operating system, you might upgrade your library. Auto-update might update something for you. You might have a hardware fault, you might have a software fault, you might run it on a different operating system. You might, a helpful colleague might edit your code in the repository for you without your notice. Obviously in a way that could only possibly improve it. And maybe it did improve it, because maybe your first answer was actually wrong. And those are just the things that can happen inadvertently. Advertently, if that's the word, deliberately, you might change your code when you pass one new data set through and discover that it doesn't support this case. Or things like that. Obviously changing it in a way that couldn't possibly change the results on the original data. And yeah. So this is what I call TDDA level 0. And we have some tooling which, a form of it is available on GitHub. It's not very well documented yet. We will make a better version available in the next few days. It's an extension to unit test. I know everyone hates unit tests, except I quite like it. And this is an example of running it on some graph generation code where one of the tests is failing. One of the graphs that's being produced is not the right result. And what you notice is it doesn't just say assertion failed. And it does do that. It tells us that our file check failed. But then it rather helpfully tells us what the diff command is to compare the actual output with the expected output, so that we can do something. And maybe we use diff, maybe we use open, maybe we use open diff, whatever.
Just to be clear, you generated an SVG. Is this a graphical graph?
Yeah.
The diagram?
Yeah.
Probabilistic.
Yeah. No, I'm a big believer in really testing the real outputs. Absolutely. Another thing on this, it says note exclusions, copyright. So one of the things when you're testing more complex things like this is often there are going to be changes from run to run because the version will change, the copyright notice will change. It'll turn out to have matplotlib is incredibly fond of using random identifiers in things that you have to ignore. It also reorders things in ways that I don't understand. So you may have to do some pre-processing, and this extension to unit test supports all that stuff, so it allows you to declare what are the semantic things you care about. It does that through pre-processing, so as well as giving you the diff on the raw output, it also gives you links to the pre-processed version so that you can see the things that have only got meaningful differences between the things. So the idea is then you harness your Jeremy Paxman mindset and go off and decide whether this is actually a meaningful change or whether it's just that you've changed the format or a library's changed the SVG is different but the graph's the same, or whatever the output is. And then there's the incredibly dangerous but incredibly powerful option to run it again with -w, and what -w means is write the outputs that you actually get this time as the reference outputs, and then when you run it again, those will be used. And of course, if you abuse that, this stuff won't help you, but if you use it responsibly, that'll be brilliant. You run it again, and this time it'll pass. So that turns out to be important. As I say, there's a version of that available on GitHub. We will document it and make a better version available soon. So that's level 0. Level 1. The next big idea that we've got is the idea of constraints. And what I mean by constraints is there are probably lots of things that you know ought to be true of your input data and of your output data and possibly of intermediate results as well. And it'd be really nice to check that those things are true when you run your analysis. So examples of that might be single field type stuff. If you're working with ages, they probably shouldn't be bigger than 150. Probably your age should be an integer or at least a number. If you've got a customer identifier, it probably shouldn't be null. If you're in a customer table, it probably ought to be unique. You might have dataset constraints. Maybe this dataset must include a CID field, and maybe some particular dataset, like the periodic table, has to have exactly 118 records. And there might be row-level constraints across your data set. So maybe start dates should never be bigger than end dates. Though, of course, everything to do with data is a world of pain. Or, if you've got columns, corresponding to force, mass, and acceleration, given that Isaac Newton told us that F equals ma always, subject to Einstein, then maybe F ought to equal ma to some level of accuracy in your data set. Whatever it is, stuff like this. And this is great. If you do this, this is fantastic. The only problem is, put out your hand if you want to write a set of constraints like this for each of your data sets. I suspect, not a single hand going up. No one does this. No one wants to do this. So our second idea is let's try and generate these things automatically. So here is the periodic table down, or the start of the periodic table downloaded from Wikipedia. And we have our software, which is proprietary, Boohis, Miro that will also generate these, but we will be, over the next few months, releasing an open source version that works with pandas and with databases and things. Don't hit them too much. So if you run this discover command, it just mindlessly goes through and finds out facts about the data set and spits them out in the form of constraints that can be executed, that can be checked and produce either warnings or errors if they're not true. So the first thing it does is it goes through and says, well, in this table, there is a field called Z, there is a field called name, there is a field called symbol. The total number of fields is 16 in this data set. Right? Then it goes through each field and says, well, Z, the atomic number, that's an integer field, so I'm going to assert that must be an integer. And it runs between 118 or 1 and 118, so I'm going to say that it shouldn't ever be less than 1, and it shouldn't ever be bigger than 118. And obviously, if we do get a new version of the periodic table, it might well go up to 119, so this might not be a good constraint. But the point is, you didn't have to do any work for this, it found it for you, and you can modify it and just delete that constraint. Or run it and delete it if it turns out not to be true on the next version of the data. It's also asserting that there are no nulls in this field, and that every value is unique in the number. It goes through, does a bunch of things like this. It does some data set constraints as well. It tries to be just very slightly smart about strings and figure out, is this a low cardinality string that probably you're only allowed these values, or does it just look like free text? And it gives you a tabular view as well, and then you can run it and get it. And one of the interesting things about this is not only are the constraints it does spit out interesting, but the constraints, it's the old curious incident of the dog in the night time. The ones it doesn't spit out are interesting too, because if it doesn't tell you that your customer number is unique in your customer table, that means you've got duplicates. If it doesn't tell you that your customer number is non-null, that means you've got nulls. So the idea is you run this, you either delete the constraints that don't make sense or modify them to make sense, or you just run it again on your next data and delete them at the point when they fail, if they are allowed to fail. So that's the idea of TDDA. Thank you for your attention. To summarize, the idea, as I say, is to take the ideas from test-driven data analysis and make something of them in the context of, test-driven development and make something of them in the context of data analysis. Two concrete ideas at this point, which are the idea of the reference test and the idea of extending the unit testing framework to support these reference tests with differences and rewriting of results and all the things that are useful like that. And there is embryonic code available, and better code available. And then this constraint generation stuff is a very concrete way of helping us do the stuff that we can't be bothered to do, but it's really helpful when we do it, particularly in the context of feeds. That's what I have to say. I'm sorry I've talked too long. I'd be very happy to take questions now or afterwards.
Thank you very much. 6 minutes for questions, then lunch.
Did you see Alex's talk on the hypothesis library yesterday, and if so, how is that?
I didn't, though I have been talking to David McKeever, not David McIver.
Okay.
Who was there. And I am planning to go to this workshop tomorrow, and I have use of it. I think there are...
No, the workshop is on Monday, not tomorrow.
I'm sorry, on Monday, not tomorrow. And David and I are talking to try and understand how much similarity or otherwise there is. To my mind, the constraint generation stuff, and particularly the row-level constraints, look remarkably like some of the sort of proxy-based testing that hypothesis is all about. The big difference being that it's very strongly constraining your inputs as well as your outputs. And it's not using fast data, it's using real data with real distributions. Now, there